1785, Charles Coulomb developed Coulomb's law, which relates the amount of electrostatic force between charges. All right, you do not need to memorize for the CK 6 times 24 times 10 to the 18th. Turn to your neighbor and tell them what that value means. What's it represent? Hopefully you said that this represents the amount of charge in 1 Coulomb. Charge of proton, charge of 6 quintillion electrons or protons. All right, you do not need to memorize this number for the CK, nor do you need to memorize the date. Just letting you know in the ballpark framework of time where we're at. We're in the 18th century. So Charles Coulomb developed Coulomb's law, which relates the amount of electrostatic force between charges. You perhaps have been reviewing your study guide, as you should, a few minutes every single night, and maybe something's ringing in your mind of, Charles Coulomb developed Coulomb's law? Did he? Did he really? If you take a look at page 2 of your study guide, where you have your continuing DCIs, disciplinary core ideas, and the rubric on which you will be assessed, right at the bottom there of page 2, Coulomb's law was not actually discovered by Charles Coulomb. It was discovered by Henry Cavendish. However, Cavendish did not publish his results, and his documents were not discovered until half a century after his death. This was lucky for Coulomb, since he received the credit and fame for this spectacular discovery. Two things. Well, first of all, this is not in any way, shape, or form to diminish the great work and experimentation that Coulomb did. There's no sense of fraud to be associated with Coulomb. And number two, the importance of publishing, the importance of turning things in on time. That's a valuable lesson, my friends, to take home with you. We have a portrait here of Henry Cavendish, and he is from the country of England. He is from the country of England. All right, back to Coulomb. Specifically, Coulomb's law states the force between 2 point charges. Now we have this Q1 and Q2. All right, we started this session looking at the SI unit of charge. The SI unit of charge is the Coulomb. However, your symbol for charge, not symbol for unit of charge, but the symbol for charge itself is Q. The SI unit of charge is the Coulomb. Your symbol for charge is Q. And remember, in physics, we always like to sound as smarticle as we can, so we say point charge. We're talking about a single charge, a single electron charge, a single proton charge. So this, very important to distinguish. I'm making up all kinds of words today. Distinguish. Just giving you time to jot that down in the study guide somewhere. The SI unit of charge is a capital C Coulomb, whereas your symbol for charge is Q. You want to keep this straight in your mind so that the formulas, symbols, units don't all become alphabet soup in your mind. SI unit of charge, Coulomb, symbol for charge is Q. All right, back to Coulomb's law. The force between 2 point charges, Q1, Q2, is directly proportional to the product of the charge. Directly proportional. The product of the charge. Ask your neighbor, what mathematical operation do you think of when you hear the word product? What is the product of 5 and 4? The product of 5 and 4 is 20. Product is multiplication. 5 times 4. The product of 5 times 4. So, if Coulomb's law says that the 2 point charges are directly related to each other, that means you would multiply the two together. Now that's the first portion of Coulomb's law. There's another portion to Coulomb's law, so we'll continue here. And Coulomb's law states that the charges are inversely proportional to the square of the distance between them. Or rather, I should say the electric force is inversely proportional to the square of the distance between them. So we have two charges. They are directly related to electric force. Directly related, so they're both in the numerator, both on top. And then inverse relationship. We've looked at a couple inverse relationships already. The Here We Go study guide, period, is inversely related to frequency. Today, in the charge study guide, we're looking at electrical force. Capital F for force, and this little subscript for electrical force. Now, the electrical force is inversely related to the square of the distance. The square of the distance. Hey, Ashley Labby, does this look familiar? 1 over d squared. And that is your inverse square law for light. The farther away you are from a light source, the dimmer it is. The great astronomer Henrietta Swan Leavitt is the one who discovered the mathematical application of this law, inverse square law, to light. This is something you looked at a little bit in the last study guide of traveling light. So 1 over the distance squared. So electrical force, inversely related. Here is a classic from the world of physical science, and some of you may know Dr. Rogers from his butter gun example, but here we have Dr. Rogers again for you, showing you electrostatic force between two metal spheres, two balls that he has suspended, and he's going to move them through 3 spans of distance. So little quick look at the inverse square law in a lab setup by Dr. Rogers. I need to get me a lab assistant.
There we are. Force is at 1 span. Please record it. Between 23.
Hey, lab assistant, record this stuff for me.
It's just about 20. Settle down. It'll be 23.7. Now 2 spans, please.
Yeah. Definitely need a lab assistant in my life.
Oh, force is much less. Well, what did you expect of an inverse square law?
I mean, seriously, what did you expect? It's an inverse square law. Of course it's going to go down. One more time.
Well, what did you expect?
You know it's serious when he takes his glasses off and looks at you.
Well, what did you expect?
Oh, of course. All right, so the formula for Coulomb's law. We have these 2 portions to Coulomb's law. We have the fact that electrical force is directly related to the product of the 2 charges. And we also know from the statement, electrical force is inversely related to the distance squared. Now we combine these 2. We're going to have the electrical force is directly related to the product of the 2 charges and inversely related to the distance squared. All right, or more neatly, as how you might see it on a reference sheet that you'll be given on all your CKs, more neatly like this. That's interesting. Didn't write that down before. That is the symbol K. The symbol K is what we call a proportionality constant. So tell your neighbor, is this ever going to change? Constant? Remains the same? No, your proportionality constant is never going to change. And what should we call the proportionality constant for Coulomb's law? Hey, let's call it the Coulomb's law constant. All right, this K value. What the K value really is, a little side note if you want to be extra smarticle today over the dinner table with family, and what did you learn at school today? Say, hey, I learned that the 1 over 4 pi times epsilon naught is a k value. And this k value represents what we call the permittivity of free space. Yes, I did feel especially smarticle saying the permittivity of free space. And essentially what we're saying here is this epsilon naught value is just saying, hey, can electric field lines, can electrostatic force flow through in a vacuum? And so this value actually turns out to be 8.9875551 times 10 to the negative 12th. Whew, all these wonderful numbers. We love scientific notation. All right. More than you ever want to know about the k value, I'm sure. So really the way you want to think about what is this k value, who cares about permittivity of free space and can it allow for electrostatic field lines forces to flow in a vacuum? Essentially think of the k value as like, hey, what type of medium are these charges in? All right, we're going to be dealing with things on Earth, so let's just assume this is a value for charges on Earth. Okay, the k value that you're going to use in this class is something you don't need to memorize. It will be given to you on your reference sheet right down there. So k is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. Ooh, that is quite the jumble of units. We're going to tackle that a little bit later on. Be aware that if you were to take some more physics at the college level, because I know many of you are taking this class for the Regent Scholarship, because you want to go to college, and so your college professors may have you do 8.99 times 10 to the 9th, but hey, we are going to go with 9 times 10 to the 9th. It will always be given to you on a reference sheet, so again, not something you need to memorize. All you need to know about the proportionality constant is, hey, let's not forget it in the equation. Now, I don't want to step and plug numbers into the equation just yet. I want to make sure that you understand the relationship of Coulomb's law first of all. Remember that electrostatic force directly proportional to the product of the two charges, and your electrostatic force is inversely related to the distance squared. Keeping these two thoughts in mind, let's have you approach page 11, learning the law. It's only 2 questions. Yeah, only 2 questions. We love teachers put A, B, C, X, X, Y, Y, Z, Z. Okay, so number 1, diagram over here is a hydrogen atom. Label the proton in the nucleus with the plus sign. Done. And the orbital electron with the minus sign. Done. 1b. The electrical interaction between the nucleus and the orbital electron is a force of, okay, are these repelling or attracting one another? I'm going with attraction. According to Coulomb's law, yep, check, check. If either of the charge of the nucleus and the electron were greater, the force between nucleus and electron would be, Let's have you in your labby ponder these questions together. Go through these questions together. Let's see how you fared. 1c. According to Coulomb's law, if the charge of either the nucleus, so the proton, or the orbital electron were greater, increase, the force between the nucleus and the electron would increase as well, would be greater, because it's a direct relationship. Direct relationship between the charges. One goes up, the other has to go up, and vice versa. If the distance between the nucleus and electron were greater, the force would be... Well, this is how I think about Coulomb's law. I think of Coulomb's law as the law of chaperoning, the law of dating. So, distance. When you are at a dance and people aren't just jumping up and down in the air or hanging against the walls and maybe actually dancing together, when the chaperones intervene, it's because you're probably dancing too closely. They recognize that the closer that two objects, charges, bodies, masses are, the greater the attraction there is. So to reduce that amount of attraction, they increase the distance between. So if the distance between the nucleus and the electron were greater, so the distance is increased, the force would have to be less because it's the inverse relationship. The farther apart, the less attraction. Inverse square law for light, the farther you are from the light source, the dimmer it is. If the distance between the nucleus and the electron were doubled, say the distance increases, my distance increases, so inverse relationship, my overall electric force, if this goes up, has to go down. So if the distance between nucleus and electron were doubled, the force would be, well, I know that if this is bigger, this has to be smaller. So it's not going to be greater, has to be smaller. Now I need to think, is it going to be a quarter as much or a half as much? This is where Dr. Rogers would take the glasses off and say, well, what did you expect? It's an inverse square law. Square law. So if the distance is doubled, square of double, square of double, square of 2, a fourth as much, a fourth as much. Let's give you a moment to reconsider, possibly, reaffirm the work that you did on 2A through D to ensure that you are remembering the square, the inverse square. Take your glasses off. Well, what do you expect?
Well, what did you expect?
Let's check 2. Consider the electric force between a pair of charged particles a certain distance apart. By Coulomb's law, if the charge on one of the particles is doubled, so electrostatic force directly proportional to the product of the two, and electrostatic force inversely related to the distance squared. If the charge on one of the particles is doubled, the force is, what direct relationship? One is doubled? Doubled. If instead the charge on both particles is doubled, 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 the force is quadrupled. If instead the distance, all right, so looking at distance, if instead the distance between the particles is halved, so the particles will get closer together, closer together. So that means your electrical force has to go up. So it won't be unchanged, it won't be less. Now we have to think about doubled or quadrupled. Okay, so if the distance between the particles is halved, square, it's going to be quadrupled, quadrupled, quadrupled. All right, if the distance is halved, all right, so that was this one here, if the distance is halved, and the charge of both particles is doubled, the force is, all right, so both charges are doubled. So a double times a double, that is a 4 times increase. Oh, just like here, 4 times increase. And then if the distance is halved, oh, that one's right here we just did. That was a 4 times increase, so 4 times and 4 times, 4 time increase, 4 times increase, 16 as great. 16 is great. If you had the answer of 8, 4 plus 4 is 8, take your glasses off. What did you expect? Okay, this inverse square law. I'll tell you the number one thing students forget with Coulomb's law is to square the distance. That's why I'm making a big deal about, well, what did you expect? Don't forget to square the distance. So this is 16 times as great. Learning the law, you were thinking about the amount of charge, the distance between charges, and how those things affected the amount of static force, the amount of force that those charges can exert on objects, or distance between those charges, that electrostatic force between them. The information we're going to continue with on page 10 is going to be doing more specific calculations. Instead of just talking generally of amount of charge, distance between, we're actually going to consider, okay, if I have this amount of electron charge and it's this distance apart, we'll give a specific value for the electrostatic force instead of just saying the force increases or decreases. On page 10, to make sure you have the formula listed for yourself. Electrostatic force directly proportional to the product of the charges. Q is the symbol for point charge. And electrostatic force inversely proportional to the distance squared. And the K is a proportionality constant, something we need to put in to define that the electric fields, electric energy, is able to exist in the medium of planet Earth. The units for force, are named after Sir Isaac Newton. So it is the capital N for a Newton. That is the SI unit of force. Now, as we had you become one with the meter, get a sense of how the distance of 1 meter feels between your two hands, 1 meter, and the liter, the gram, the kilogram. I'm going to give you a sense or an idea of how much a force of 1 Newton is. A quick way to think about it is if you were to hold an apple in your hand. The apple is pressing on your hand with a force of about 1 Newton. So that is not a lot of force. 1 Newton, very small amount of force. Now, speaking of Newton, apple, Master Levy, is that legend, myth, folklore, or fact? The apple fell, struck Newton on the head, and he had some wonderful epiphanies about gravity. In Physics B, your first study guide will be about the life and work of the scholar Sir Isaac Newton, and your Physics B instructor will let you know if it's fact, fiction, legend, folklore, or myth.